Okay, so we are looking at MQ 4.1. My ink's almost dead on that. Now we'll keep going. 4.1, number 4. And really what we're going to do real quick is we're going to do a kind of like the way I set up stoichiometry thinking. So do me a favor, go ahead and read the problem real quick just so we can get the problem set up on the board.
You add 24.06 milliliters of 0.2 molarity barium hydroxide to 30 milliliters of 0.26 molarity hydrochloric acid. If necessary, and then it just says enter the formula for the chemical species predominantly present in solution that will determine the pH.
Now, did I miss, were they both 0.26? Did I miss a number there?
One of them is 24, no, that's correct.
Okay, one's 0.2 and one's 0.26?
Yeah.
Okay. I thought I just missed a digit.
Like definitely from there, that's where you gotta do the stoichiometry, because from there, you could think that the limiting reactant would be barium, because you see like, oh, there's less, and like,
yeah,
already, but.
So, a couple things we noticed. First off, we noticed that this is strong acid plus strong base.
Yeah.
So we know this is going to totally react. This is going to be, I'm going to put totally in quotes, right? Because it's always in quotes. But this is essentially saying, look, with a strong acid, strong base, the conjugates I produce are not going to have any noticeable equilibrium. So I can just do this like stoichiometry. So we go ahead and we can set up our chemical reaction. And I'm going to do this just like a problem from 127. So I'm going to have wrong thing doubled. Good start. We're going to have barium hydroxide plus HCl goes to, just to make it, I should always put a double arrow, but because I know this is going all the way towards products, I'm putting a single arrow, even though it makes me feel weird.
Yeah.
I'm going to make barium chloride, and I'm going to make H2O. Barium chloride is going to be aqueous. It's aqueous. We're doing this with an aqueous solution, so the barium hydroxide is already aqueous. The balancing coefficients would be a 2 in front of the HCl, a 2 in front of the H2O. Then we go ahead and we can do this. And I'm going to do this the long way first, and then we'll go look at the table way that I like to do it. So we'll look at this in 2 steps. So, doing stoichiometry, the way most of us learn it in high school, the way most of us learn it in probably other classes as well. We're going to take our 24.06 times 0.2, and that's going to get us, and let's put units on this, milliliters times 0.2 moles barium hydroxide for 1 liter. And I can go ahead and I can do divided by 1,000 milliliters per liter. That will get me, so everything works out, and that will get me my moles of barium hydroxide.
0.002632.
Then we do the same type of thing for our HCl. We do our 30.
Oh, I'm sorry, that's actually wrong. It's 0.0048 moles. Yeah. I was looking at the wrong thing.
No worries. We do the same thing for our HCl, 30 milliliters, 1,000 milliliters per liter, times our 0.26 moles HCl per 1 liter.
That is 0.0078.
We look at this, and most people's hunch is to say, oh, barium hydroxide is limiting because it's the smaller number. And that works as long as we've got 1-to-1 mole ratios, because then the amount that you have is the amount that you use and everything's fine. Here, we've got a 2-to-1 ratio. So the part that I have written in black, the chemical reaction, essentially is telling us that's the recipe. That's the ratio at which things get put together. That's the ratio at which things are going to combine to make a chemical reaction happen. Whereas the amount of things I have to make that happen are the numbers in green. The analogy I love for this is you can look up a recipe in a book. How many times can you do that recipe?
As many times as you want.
Well, depends on what you got in your cupboard.
Oh yeah.
Right? So this is like the recipe in the textbook.
Yeah.
This is what you got in your cupboard. So that's going to restrict how many times you can do the recipe. Now, of course, you can go to the grocery store and buy more simple. Sure, you can do it as many times as you want, theoretically. But if you're just doing it tonight, store's closed, it's just whatever you have in your cupboard. So here's what we've got to work with. This is the ratio at which they go together. There are 3 different ways to determine limiting reactant. 124, yeah. Yeah, so this is 129, by the way. We'll be doing this later in the quarter, though. There's 3 main ways to determine limiting reactant. There is moles, theoretical moles produced. There is theoretical moles of reaction. There is, one of my least favorites, guess and check. And then there is, after you get good at those 3, there's the way most of us do it, which is you just do it in your head. So I look at this and I'm like, oh, barium hydroxide is definitely limiting. How did I do that? Well, I know it's a 2-to-1 ratio, which means my HCl needs to be twice as big, but if I doubled my barium hydroxide, that'd be like 9.6, and I don't have 9.6, I've got 0.7, I've got 7.8. So let's do it with math, though, so we can see it rather than just doing it in my head. That's like our goal, is to eventually be able to kind of look at these things. And every once in a while, I get a problem where I can't do it in my head, and I still have to do it this way. And my favorite way is moles reaction. This is a 129 problem, by the way. So I'm going to check for my limiting reactant, and I'm going to calculate my moles that could, how many times the reaction could happen. So with 0.0048 moles of, whoa, that's a weird B, barium hydroxide, every one time the reaction happens, it uses 1 mole of barium hydroxide. So that tells me the reaction can happen 0.0048 mole times. For my HCl, I've got my 0.0078 moles HCl. I'm kind of crunching my writing so it can fit in. But every one time the reaction happens, I use 2 moles of HCl, right? Because one reaction has 2 HCl in it.
Yes.
So that means for the HCl, I can only do this. I need to my calculator.
0.0039.
I can only do the reaction 0.0039. In this situation, the smaller number, we can see how this smaller number comes up when we're doing our stoichiometry in a moment. But that smaller number is essentially going to ID our limiting reactant. It tells us that the limiting reactant, right, if I look at my barium hydroxide, I could do the chemical reaction 48 times. You know, it's 48 times 10 to the minus 4 times. If I look at my HCl, I can only do the reaction 39 times. 39 times 10 to the minus 4 times.
Yeah, and it's important that we do that reaction step, because otherwise we might think that barium hydroxide is the reactant.
Yeah, so that we could pick the wrong limiting reactant if we're not careful.
Yeah.
And honestly, like, I should probably do it this way every time, because if sometimes when I do it in my head, sometimes I'm having days where my mental math is on point and I'm like, cool, I got it. And other days I'm just like, nope, I missed a 0. Or like, my common one is I'm dividing by 2 and I end up multiplying by 5. Or like I end up multiplying by 2 because I'm like 1/2 is like 0.5, and like I just mess it up sometimes. And I get the wrong one. And that's where the guess and check method comes in, and we'll talk about that in just a moment. But guess and check can waste a bunch of time if you're not careful. So here we've got our limiting reactant. We've got our chemical reaction. Now, the traditional way that most people learn how to do stoichiometry, whoa, is not this. This needs to be erased. the traditional way. So I'll tell you a quick funny thing while I'm erasing this. During COVID, when I was making like lecture videos, I would pause it and I would flip the board, and I had a video at some point where I flipped the board like 6 times and there was something different on each time. But because of the way I edited the video, it just looked like the board was endless. It was fun. I just remembered that right now because I was like, oh, I should pause the video now. So, okay, so the typical way that we learn to do stoichiometry is we do moles start minus moles reacted That's going to get us our moles excess or our moles produced, depending on whether we're looking at reactants or products. Okay, so that means if we wanted to do barium hydroxide, right, I've got that, how many was it, 0.07?
So don't we start, 0.0078 moles HCl.
Oh no, what's the other one?
Oh, the reaction 0.0039.
Well, no, what's the moles of barium hydroxide?
Oh, 0.0048.
Okay, so I'm going to have 0.0048 moles barium hydroxide.
That's the total.
That's how much I start with. I know it's my excess, so that's why I'm doing this one. If I did HCl, it should come out to 0. Then I'm going to subtract off. Now, how many moles of barium hydroxide reacted? That's going to be my 0.0078 moles HCl. And then I'm going to get my moles of reaction. I'm going to have 2 moles of HCl for every reaction. And then, but for every reaction, I'm going to use 1 mole barium hydroxide. So you notice inside of this mole ratio, the limiting reactant is always on bottom, because moles of limiting reactant divided by its coefficient is essentially getting us that 0.0039 number, right? It's getting us that moles of reaction. But for every reaction that happens, I use 1 mole of barium hydroxide. So this will get us how many moles of barium hydroxide. This number with this fraction will get us how many moles of barium hydroxide are reacting. It also works out really nicely in the units. You notice here I've got moles of HCl, moles of barium hydroxide, not the same units. But here I can cross out because of that mole ratio, which tells me how the HCl and the barium hydroxide relate to each other. I can cross those out, and I can get a number for how much excess barium hydroxide I have. If I didn't drop my calculator. 0.0078 divided by 2 gets us to 0.0039. Negative plus 0.0048. That gets us 0.1239 moles.
Is that the same thing as 9
times 10 to the minus 4?
Okay.
Yep. Now, at this point, we say, okay, does that make sense? Does this work? This is where the guess and check method comes in. If we were doing guess and check, if we were just like, I'm just going to pick, there's 2 options. I'm just going to pick one and check. If you do everything else correctly and you get a negative amount of moles left over, you picked the wrong thing. You can't have a negative number of moles excess. That just doesn't make physical sense. It's like your reaction used up things that aren't there, created antimatter. I don't know. Like, it doesn't make sense. You just made a mistake in your choice. So now you'd have to go back and choose the other one and go through the process again. Now, the way that I set up my math, and this is where you went wrong in yours. You messed up your mole ratio, but we'll get into that in just a moment. The way I set up my math is I say, look, I can do things in this sentence way, or I can do it in the column way. Or I've got 0.0048 minus 0.0079 times my 1 to 2 ratio gets me 0.0009. All the same stuff, right? It makes the unit analysis a little bit more difficult, but once we're comfortable with the unit analysis, this way fits really well underneath our table, where my starting amount is that 0.0079. Oh, got that backwards. 0.0048, 0.0079. And this is why I like this method. So, right, technically at this point, start reaction excess, I would have to do an expression like this for each one, where I'm thinking, well, how much did I start with for that particular component? There's 4 things in the reaction, so I have to do this 4 times. How much of that thing did I start with? How much of that thing reacted? How much did I make? Right, and I do that 4 separate times, once for each component. It takes a long time. It's essentially doing the same thing. The reason I really like doing it in this table way is because it splits up the thinking rather than in terms of each component, in terms of the process of the reaction. I start with, where's my reaction? What's the starting point of my reaction, right? So I think about all 4 things and where they're starting. After I have those 4 things and where they're starting, I'm like, okay, what could possibly happen? I've got my chemical reaction. How is this going to proceed? I already know my limiting reactant because I did some separate thinking, and I'm going to have my limiting reactant. As the reaction goes, my reaction is going to happen this number of times. So I know my reaction is going to be minus 0.0079 times something over 2, minus 0.0079 times something over 2. On the product side, it's plus 0.0079 times something over 2, and it's plus 0.0079 times something over 2. Right? The reaction, the number of times the reaction is happening, I can take that into the reaction step. Now, this one, since I'm looking at barium hydroxide, I think it's a 1 on top. You know, it's a 2 on bottom of all of them, because that's limiting coefficient and limiting reactants on bottom for all of them, because that gets us how many times the reaction happens. Here I'm looking at my hydrochloric acid. I use 2HCl for every time the reaction happens. Here I've got 1 mole of barium chloride produced for every time the reaction happens. 2 moles of water produced.
That's what really confuses me, that fraction.
Yeah.
Could you explain it a little further?
Yeah, so that fraction is just the mole ratio.
Okay.
Right, and I'm just being really, I'm hiding my units. It's this thing, 1 mole of barium hydroxide per 2 moles of HCl.
Okay.
Is the ratio at which the HCl relates to the barium hydroxide. So that 1 to 2, this 1 to 2 is saying this is moles of HCl. So I've got 1 mole of barium hydroxide for every 2 moles of HCl reacted.
And for that one, it's 2 moles of HCl for every 2 moles of HCl.
Yeah. This one?
2 moles of HCl for 1 mole of barium. Okay. 2 moles of HCl for 2 moles of water. Okay.
Yeah.
So I think if I write the units, that's going to make a lot more sense.
Yeah. And me, I usually, I think I wrote the units the first day we were doing this in 129. And at that point, I was just like, you all know the units. I'm going to do this faster.
Okay.
So then we get our HCl, of course, goes to 0. If it doesn't, it's not our limiting reactant. We've done something wrong. If it's negative, we've definitely done something wrong. Our barium hydroxide, I already forgot. Oh, no, I remember now. 0.009, and this becomes 0.00388. No, this is, oh, sorry, I messed up my numbers. These are supposed to be 7 8s.
Yeah. And the other one 0.0038.
Yeah, I messed up my 8 and my 9, and this is 39. Yeah. Sorry about that. So if you were wondering, where'd you get 0.0079? Typo.
And then for a table like this, we do include the liquids and the solids.
Yeah, because this is stoichiometry. This is not equilibrium.
Yeah.
So now we've done our equilibrium. Now, not our equilibrium, our stoichiometry. And that's stoichiometry. That's it.
So it's start, reaction, and then
excess.
Okay.
I used to write start, reaction, end. I was trying to make it spell something, and then a student told me to make it say stress.
Yeah.
So you got your ice tables and your stress tables.
Yeah. Okay. Got it. Now it makes more sense.
Okay. The last step, there's one last step. So that's all 124, 127 stuff. Eventually, we're not there yet. We'll get there in a week or 2. Yeah. But this problem is asking what's the pH of the solution. So there's one last step.
Yeah, so we can take the moles of excess of barium hydroxide. And then we can put that over the total volume.
Oh, we gotta be careful about that.
That's what I did wrong, probably. Because of the ratio, right? Yeah.
Mm-hmm. We have to take the molecular. So this is the mole ratio, the molar ratio, we can also do the molecular ratio of how many hydroxides for every molecule that falls apart.
So yeah, that's the 0.0009 moles of barium hydroxide times 1 over 2. No,
2 over 1.
2 over
2 over 1. So we end up with 0.0018 moles of OH minus. Now you can go ahead and take the negative log to get your POH, and then 14 minus that to get your pH.
Yeah, okay.
Is that good?
Yes.
Okay.